Hello team, can you hear me?
Hello, good morning.
Yes, we can hear.
Good morning.
Hello?
Hello,
Hi
good morning.
Ibrahim. Good morning.
Hello, good morning. How's it going? Could you please open your camera? Yeah. Okay, welcome you all to the IADC workshop course. This is Ibrahim Abu Zaid, accredited dual control instructor and assessor for IAWCF and IADC workshop. Today we are going to be together in the IADC workshop course. But before getting started and sharing our presentation, I need to get to know you more. So, Miss Anna, could you please introduce yourself?
Okay, my name is Anna. I'm working in SLB for almost 9 years. Since 2017, I'm working as a well engineer in IPM. So for now, I'm working together with Roman and Georgi in Uzbekistan.
Nice to meet you. Mr. Georgi.
Hello, Mr. Ibrahim. My name is George. So I'm working in SLB since June of last year. Before I work at the Gazprom and several companies as a drilling supervisor. So I'm glad to see you and happy to join.
A pleasure having you. It's a pleasure having you here. Mr. Roman.
Yeah, good morning everyone.
Good morning.
So,
Good morning.
yeah, I'm on the same project with our team here in Uzbekistan. My current position is drilling superintendent and 20 years in Schlumberger. Nice to meet you.
Okay, nice experience. Okay, let's get started and to avoid wasting time. Is the presentation shared? Presentation shared. If the screen is shared?
Yeah, we can see the screen, yes.
Yes, okay. Okay, today we are going to discuss the first part of the well sharp course. It's about the principles and procedures. Principles and procedures and equipment. It's a division related to the or belong to the IWCF. But in the IADC workshop, we are going to get started by the first part, which is B&B, principles and procedures. Tomorrow also we'll complete the second part of the B&B, and in the third day we are going to discuss the equipment. And fourth day, as we mentioned in the WhatsApp group, we are going to discuss the simulator training. Okay, let's get started. As you know, at the beginning of oil discovery, people used an old drilling techniques like cable tool drilling and spring pole drilling. After that, Mr. Edwin Derrick came and invented this must. And he's considered as the founder of modern oil industry. Then people in this era faced many problems like a blowout because there's nothing used to close or shut in the well. Till Mr. Harry Cameron came in 1922 and invented the first POP in history. This is the first POP in history. It was WARAM, no annula. The IWCF, API, and IWCF and IADC, which are came or appeared and set the rules of the IWCF or set the rules of well control in general. And the first rule set by them, it's a double barrier. We must have in all operation double barrier. So what is the meaning of barrier? The barrier is the first that an object that prevents unplanned flow from formation to surface. And double barrier means we must have a primary barrier and secondary barrier. The primary barrier it's not always the hydrostatic pressure or maybe it's a cement plug. So in general, we call the primary barrier as the first object. the first object that prevents unplanned flow from formation to surface. It's not always the hydrostatic pressure or the mud weight. Maybe the first object that faces the formation pressure, it's a cement plug. So to be more accurate, the primary barrier is that the first object that prevents unplanned flow from formation to surface. The secondary barrier, it's the second object that prevents unplanned flow from formation to surface. Usually it's POP. Barrier classification. We have a classifications for barrier or barrier types, like a hydrostatic barrier. Hydrostatic barrier means the hydrostatic pressure coming from your mud weight. Mechanical barrier, like a BOP. Physical barrier, like cement. Procedural barrier, like recording and gain and losses by the directman to know the case. Barrier envelope. This idioms or terms that set by the IWCF and IADC with sharp. Barrier envelope, it's more than one barrier acted as a system to prevent unplanned flow from formation to surface. The same definition. But if you shut in your well and you have a leak from your wellhead, what is the benefit from this shut-in? There is no benefit. There is no control. So you have a defect in your envelope. So the barrier envelope, for example, everything can see a pressure. It's called the barrier. If you have a cement is a barrier. Casing is a barrier. Wellhead is a barrier. Gasket, even the gasket in the wellhead, it's a barrier. Everything can see pressure. It's called, or it's included in the term of the barrier envelope. And here we have the most important question here. We can say this object acts as a barrier. And here I need your share. Miss Anna, could you please tell me your point of view about this question?
And by this object, what do you mean? When the barrier envelope or what?
If I tell you the choke manifold is a barrier or remote choke is a barrier, how can I say this choke or remote choke or adjustable choke acts as a barrier? The IWCF,
It should be tested, verified, checked.
Yes.
And it should be, I think, together with another barrier that is in contact with the fluid itself for the formation fluid, I mean.
Yeah. So it must be tested. To verify this object or any object acts as a barrier or not, it must be tested. So we have a positive test. Positive test means you can operate your pump where? In the direction of flow. For example, we have a full opening safety valve. You can apply pressure from above and from below. Okay. From which direction it will be accepted by IWCF according to the criteria that's set by the IWCF and IADC will show? From the direction of flow, from below. So I can conduct or I can apply pressure from above and from below on the full opening safety valve, for example. But it's accepted from the direction of flow. This direction of flow called upstream or formation side. Okay. So if I fail to conduct a positive test, to test this barrier, to make sure it's a barrier, to verify this object acts as a barrier. In this case, if you fail to apply a positive test, just apply a negative test. What is the meaning of negative test? The IADC will show and IWCF inserted topic called liner lab. This liner lab, it's an application about what? About the negative test or inflow test. So here we have a negative pressure test or inflow test. After running your liner and making your cement job, here we have a bucker, a hanger, and bucker. Liner, hanger, and bucker. The combination of hanger and bucker called liner lab. We need to test this liner lab. Is it acts as a barrier or not? So after the cement after the same job here, Mr. Roman, can we apply a pressure in this direction, in this formation side, in upstream? Can we do this?
We cannot from that
No.
side.
Yeah, no, we cannot. So the solution here is to apply a negative test. Apply a negative test. Where in the downstream, this is upstream. Formation side. And this is downstream. Or surface side. How can we apply a negative test or in the surface side? Just replace your heavy mud by a light mud. But if we do this inside the well and replace all the heavy mud inside from the well by a light mud, if you have a leak from this liner, you have a cake now. Where is your clean mud weight? So it's not reliable to make replacement for heavy mud by a light mud. So what will we do is to replace the heavy mud by a light mud inside the string only by the same running tool. So after that, just set your retrievable bucket to the steps for the final vision now. You have a light mud inside the string and you have a retrievable bucket set here, and the mud by a red color, it's a heavy mud. We need to test this liner lab. Is it acted as a barrier or not? So you will have an increase in shut and drill by pressure. Increase of the shut and drill by pressure, that means you have a leak. You have a leak from this retrievable bucket or from this liner lab. To differentiate between both, to select which one is leaking now from is it a liner lab or is it a retrievable bucket, just operate your trip tank pump above the retrievable bucket. If you have a reduction in level of the trip tank, that means you have a leak from the retrievable bucket. And if the level of the trip tank is still constant, that means you have a leak from the liner lab. Make sense? Go ahead.
Yeah, so also normally after setting the packer, we can test it from top.
Yeah, it's
that packer is not leaking. Yeah.
Yeah, but the IADC and IADC will chart, it's applicable in most of contractor companies like Aramco. Aramco is doing both. Aramco in Saudi Arabia doing both. Testing the retrievable bucket and also make like what IWCF mentioned. So this criteria or this line or this it's both by IWCF and IADC will chart. So he wants to ask you a question. So he make a scenario to ask you. Okay, make sense? Okay. Mr. George, please just read the first question and select the correct answer.
Must be in place and tested for monitoring operation. Select B, at least two barriers.
Yes, two barriers.
To be implemented.
Correct answer. Yeah, Mr. Roman.
Okay, what is a well control barrier system envelope? This should be B. More than one barrier that act together. Yeah.
That's correct. More than one barrier. Yeah, Miss Anna.
Okay, you have a set liner and are now circulating the well to clean mud before drilling out the liner shoe, where potential leak path to allow formation fluid to enter the well. Drill strain, BOP, leaking liner. Okay, leaking liner, lap or shoe.
Yes.
C.
Yes, C answer. Yeah, your turn, Mr. Roman. Mr. Roman, your turn.
Yeah. Okay, what is a negative test? Just a second. Should be B.
Yes, B answer.
Mm-hmm.
The pressure here in the upstream or formation side must be greater than the pressure in the downstream or surface side. Yes, B answer. Yeah, why is negative test performed by on a cement plug or a liner lamp, Mr. George?
C, to check for cement integrity.
Yeah, integrity, the source of leak. Okay. Sana?
Okay, which of the following is considered a procedural barrier? The procedural. Maybe monitoring the well for gains or losses.
Yes, sure. Monitoring goes gain and losses. Which of the following is the physical barrier, Mr. Roman?
Physical barrier will be cement plug. C.
Yes, cement plug. Yeah. George.
Flow check was performed and the well is flowing. Which barrier has failed? Hydrostatic, not hydrostatic.
Yeah, hydrostatic pressure. Yeah,
Yeah.
not hydrostatic. C answer. Yeah. Your term, Stan.
If the key is swapped and when tripping, which type of barrier has failed? Hydrostatic barrier.
Hydrostatic barrier, yes. Yeah. So, Roman.
Yeah, which of the following is not a method of wellbore barrier verification? B. Weight set confirmation tagging.
No,
Is not a method.
it's
Wellbore
not
barrier.
it's not applicable. It's not applied, but it's set by IADC and IADC will chart. This leak of test.
Okay.
Leak of test. Okay. So this
tagging,
method to verify. And this, yeah.
tagging
Yes.
is considered as a
Yes. Set by the
barrier.
criteria. Yes.
Okay.
So negative test, positive test, and tagging. Okay. Okay. As you know, we'll talk about the pressure concepts. We have a large conflict between the hydrostatic pressure and the formation pressure. The hydrostatic pressure is calculated by this formula, 0.052 multiplied by mud weight multiplied by the true vertical depth. And this constant depends on the units of the mud weight and units of the true vertical depth. If you have the mud weight in ppg and true vertical depth with feet, the constant will be 0.052. And if you change, for example, the mud weight to PCF, the constant will change too. So the formation pressure is the pressure of the fluid which is in the pore spaces. In all operation, if I want to calculate the formation pressure, how can I know the formation pressure? The formation pressure, if you want to calculate the formation pressure, just use the same equation of the hydrostatic pressure, because the scientists suppose all formation contains a salt water. For example, the mud weight of the salt water, it's 8.95. So the formation pressure is different from area to another area. Why? Because we have a different depth, different fluid inside the pore spaces, and different stresses. But the scientists assumed that all formation contains a salt water. This is the normal. If you want to calculate the formation pressure, just use the same equation of hydrostatic. For example, if I want to calculate the formation pressure after 1 feet, after 1 drill feet, so the formation pressure will equal 0.052 multiplied by 8.95 multiplied by TVD. So at 1 feet, the formation pressure you will get this value, 0.465. So this is a pressure after 1 drill feet. So each drill feet, your pressure will increase by the same value, 0.465. At 2 feet, if you add this 0.465 to 0.465 or change this steps to 2 feet, you will get the pressure after 2 drill feet. So this value 0.465 coming from as assumption of including the drilling, the formation by a salt water, which density is 8.95. So if I want to calculate the gradient, just divide your pressure by depth, or the constant multiplied by the mud weight. If the gradient greater than the normal value, which is 0.465, it's called abnormal or above normal. If it's less than this value, it's called subnormal or below normal. Yeah. Let's discuss these questions about the last part. Yeah. Mr. George?
If you change mud weight units from ppg to PCF pounds per cubic foot, what change will you have to make to the formula? Use mud weight to vertical webs, replace different constant, use mud weight. C, replace with a different constant.
Yeah, we will, yes. For example, if you want to calculate the hydrostatic pressure using the specific gravity, not a mud weight, use just 0.433 multiplied by specific gravity multiplied by TVD by feet. Okay, and this will, the unit of the hydrostatic pressure will be with PSI. Okay, and there are a lot of units and constants. Yeah, the second question, Mr. Roman.
Hydrostatic pressure is pressure should be A, stationary column of fluid. No, sorry, C, pressure exerted by a column of fluid, yes.
Yes, correct. Yes, correct. Pressure of the fluid column, yes. Miss Anna.
Okay, through vertical measured hydrostatic, what is your mud weight gradient? Okay, let me calculate.
Yeah, okay, the gradient equal.
Yeah, I have to divide hydrostatic pressure by TVD.
Yeah, 4476 divided by TVD 852.
Yeah, it's a 0. It's B.
B amps. Okay. Yeah, if you have the density, he's asking about the density, yes, and he's giving you the gradient. So your turn, Mr. Joe.
What is the density of a fluid with a pressure gradient of 0.567 psi per foot?
Yeah. How can we get the density? The gradient equal 0.052 multiplied by mud weight. You want mud weight. So divide this by the constant. Yeah, gradient by the constant. Okay.
So it should be C.
C answer?
C.
567 divided by 0.052. Yeah, 10.9. C answer. Okay. We have 3 cases, as you know. We have the formation pressure greater than the hydrostatic pressure. That's called under balance. If both are even, it's balanced, and if the hydrostatic pressure greater than the formation pressure, It's overbalance. Okay. Look at this. Yeah, let's discuss the question first. Yeah. Miss Anna.
Okay, what is called when formation pressure is greater than the hydrostatic? Okay, it's overbalance.
Overbalance, yes. Yeah. Formation pressure is greater than the hydrostatic.
No, it's under.
Yeah, underbalance. Yes. Mr. Woman.
What is called when formation pressure is the same as the hydrostatic? Balanced.
Balanced pressure. Yes. Yeah, what is the definition of abnormal pressure formation, Mr. Roman? Mr. George, sorry.
The formation pressure that is greater than the hydrostatic pressure caused the full column of formation water.
Yeah, and the potential of getting under balance in this abnormal pressure formation is high. Okay. Okay. And the most important question here, when you have a gas inside the well, is it considered as a cake or not?
No.
No. Okay. How can we confirm we have a cake?
We need to do a flow check.
When we do a flow check. Okay. For example, if you have a swap, but before the explanation, I need your share, Mr. George and Miss Anne. Yeah, go ahead, Mr. George. If you have a gas inside the well, is it considered as a cake? Mr. Roman said no.
It will depend of what's a gas. Maybe this is a connection gas, and we cannot consider it. It is a kick, but it's if not connection or drilling gas, yeah, it's supposed to be kick.
Yeah. So your idea about the size of cake or the size of gas? Yes. Yeah. Yeah, Miss Anna.
I agree with Roman and George. For example, we can have drilled gas as well. I mean, no matter what you're gonna do, I mean, still, if this is a gas-bearing formation, you're gonna have some gas. It's inevitable.
Great. Okay. So this question leads us to know the difference between the influx, kick, and blowout. Here we have a gas inside the formation. So entry of the formation fluid into well bore called influx. And if this unwanted influx causes well to flow, that means you have kick. First, the driller will observe increase in the return flow. And this is the first sign. And the second sign, positive sign, you will have a gain inside the tanks. So if you have an increase in the return flow and gain inside the tanks, active tanks, that means what? You're a kick. You have a kick now. But entering of formation fluid into the well bore, that called influx. It's not necessary to be a kick. Why? Because increase of the return flow and having a gain, this will not happen till you lost your hydrostatic pressure. You're underbalanced. You're underbalanced now. So the entering of formation fluid into well bore, it's not necessary to be a kick. It's just influx. Maybe it's a swap like pulling out the string with high speed, and you have a small clearance between your well and your string, and you have a viscous mud. All this cause of the swap. So you got under balance, but instantaneously, not by a permanent condition. So entering of formation fluid into the well bore, it's called influx. If this influx causes well to flow, that means you got under balanced and you have a kick. The kick means you have increase in the return flow and gain inside your tank. Okay. The blowout, as you know, it's uncontrolled kick. Uncontrolled kick means blowout. Wait for the blowout. Yes. Mr. Roman?
Most formations that have to be fractured to produce contain what? Oil and gas?
Yes. What terms means an undesired influx of the formation fluid into wellbore? Yeah, Mr. George.
Term means an undesired influx of formation fluids into the wellbore. Fractured formation, lost circulation, kick, blowout. Kick?
Yes, kick. Uncontrolled kick means blowout, but undesired influx means kick. Okay, but we have a complement for this definition. Undesired influx causes well to flow. It must be mentioned. Okay, so it's a kick. Anyway, it's a kick. Yeah, kick is Sana.
It's undesired influx and influx.
Yeah. Influx of the formation fluid downward, yes. Uncontrolled flow of the formation fluid at surface. Uncontrolled flow of formation fluid at surface. Kick.
Uncontrolled, you mean? But why?
Uncontrolled means,
I would
yeah,
say
it's
it's
a kick.
blowout.
It's a kick, not blowout. It's a kick. Okay.
It's a D,
Okay.
D,
Yes.
an
The
influx.
answer. Yes. This is the definition of blowout, not a kick. Kick, you're correct. It's an influx of formation fluid down. Yeah. What term means uncontrolled flow of formation fluids? It's a blowout. Yes.
Blowout.
Blowout. Yeah. What is the bottom hole pressure? The bottom. Yeah. Mr. Roman.
So bottom hole pressure. The first one, A, total pressure exerted on the bottom of the hole.
Yeah, all pressure exerted on the bottom hole. This is the bottom hole pressure. Okay. As you can see here, we have a drilling window. Drilling window, it's the difference here between the fracture pressure and bore pressure. For example, if I tell you I will mix a mud weight, creating a hydrostatic pressure, this hydrostatic pressure has an upper limit and lower limit. The upper limit is a fracture pressure and lower limit the formation pressure. If you get below the formation pressure or bore pressure here, you will have an influx or kick. And if you exceed the fracture pressure, that means you have a losses. You'll have a losses. After that, after losses, your hydrostatic pressure will drop. Then you will have a kick. Then you will increase your mud weight again. Here we have a large drilling window between the fracture pressure and formation pressure here. Our mission here is to create a hydrostatic pressure between both, between the fracture pressure and between the formation pressure. Okay? But here, this is a large window. You can increase your hydrostatic or decrease it. But here, look at this. This zone, it's tight or narrow. In that tight or narrow window, look at the hydrostatic pressure here. If, for example, at connection in this narrow window, the driller just operate his pump. After operating the pump or bringing the pump to for drilling, the hydrostatic pressure just touch the fracture pressure, and he got losses. Then, after increasing the hydrostatic pressure after losses, it's dropped. So he's a kick. He want to solve this problem, which is a kick. Just increase your mud weight to kill mud weight. Then you will fracture the formation again. So you will continue in loss and gain cycle in this tight window or in this narrow window. The hydrostatic pressure must be in between the fracture pressure and bore pressure or formation pressure. Don't change the hydrostatic pressure to prevent the oil from getting losses, to avoid exceeding the mass, exceeding the fracture pressure. In the tight window, we have a problem. We will have a problem, which is gain and losses cycle. So maybe the conventional drilling is not suitable in the drilling of the tight window. So we have to deal with bottom hole pressure, not hydrostatic pressure, because although you didn't change your hydrostatic pressure in the tight window, you exceed the fracture pressure after operating your pump. Why? Because you have a hydrostatic pressure plus EBL. So we have to deal with not hydrostatic pressure only, deal with the hydrostatic pressure plus EBL, which is bottom hole pressure in case of dynamic. In all cases, or on all situations of B&B, principles and procedure, the first line of defense is the bottom hole pressure. So we have different equations and different cases for the bottom hole pressure like this. Bottom hole pressure in case of static, your pump is off. It's equal hydrostatic pressure only. And in case of dynamic, equal hydrostatic pressure plus EBL. In case of surge, running hole too fast, it's equal hydrostatic plus surge, and hydrostatic minus swab in case of swab, pull out of hole too fast. But while shutting the well, let's take an example here. Look at this. If you have a hydrostatic pressure inside the string 5,200 psi, and in the annulus it's 5,200 psi. This is the formation pressure, it's 5,000 only. And you have a U-tube, your bottom hole pressure here, your first line of defense here, it's 5,200 psi. Is this formation pressure able to push a gas inside the well? Yeah? Is it able to do this? No. Why? Because you overbalance your bottom hole pressure, the first line of defense, 5,200, and formation pressure only 5,000. After encountering the abnormal pressure formation, if you encounter the abnormal pressure formation or face abnormal pressure formation, its pressure, the formation pressure here is 5,400 psi. Now, in this case, you're underbalanced. You have a problems here. Yeah, so having a problems. What are these problems? The first problem is you are getting underbalanced. Underbalanced by what? How much pressure you got underbalanced?
200 psi.
200 psi. So this is the first problem. And the second problem, the formation will not let you free. The formation will not let you free. It will give you a gas. The gas will enter the string or the annulus. Will the gas annulus? Why?
Oh, because in the drill string you do have a float up. Yeah, float valve. Yeah.
It's not. Yeah, this is not the main reason. Having a float valve, you have a large area in the annulus, but you have a nozzle of the bit like this. It's very small, so the gas will prefer the large area. No gas inside the string. If you do not have, even if you do not have a float valve, the gas will be in the annulus. Okay, so we have a problem underbalanced by 200 psi and the gas inside the annulus. Inside the annulus. Okay, what is the action of the driller? Now, if you have a gas inside the well, the gas will enter the annulus. The hydrostatic pressure inside the annulus was 5,200 psi. The mud is replaced by gas. So entering the gas in the annulus affect the hydrostatic pressure of the annulus or the hydrostatic pressure of the string?
In the annulus.
in the annulus. So let's assume it will be 5,100 psi. 5,100 psi. So entering the gas inside the annulus reduces the hydrostatic pressure of the annulus by 100 psi. This 100 psi, it will be compensated by the shut-in casing pressure. So the action of the driller now, if the mud inside the annulus is replaced by gas, that means you have a return flow. Then you will have again inside the tanks. The first action of the driller is to shut in the well. And the benefit of shut in, look at this, shut in the well. What are the benefits of shut in the well? If you let the gas open, let the well open, if you did not shut in the well, what will happen to the gas? The gas will expand, will still reduce, or continue in reduction, continue in expansion, and this expansion reduces the hydrostatic pressure. So if you shut in the well, you prevent the behavior of gas, which is expansion, no gas expansion. So this expansion of gas followed by what? Followed by hydrostatic pressure reduction. After that, increase in the casing pressure and increase in the bit gain too. So the first benefit of shut-in, no gas expansion. No gas expansion. What is the second benefit? Yeah, I need your share. What is the second benefit of this shut-in? You shut in the well now. Yeah, Mr. Roman.
So I will prevent further
expansion
and influx.
Okay, yes. No secondary influx will enter the well.
Yeah.
That will happen by shut-in. Okay, but this shut-in makes a stabilization for the well. We have two sides, annulus and string. We have a stabilization. This stabilization creates the bottom hole pressure equal the formation pressure. So no secondary influx will enter the well again. Look at this, bottom hole pressure equal the formation pressure. So let's do it. The bottom hole pressure here, it will be 5,400 psi by shut-in. If I tell you I have a shut-in well and the formation pressure or the bottom hole pressure is 5,400 psi, you will understand directly this is the same of the formation pressure. The formation pressure will be the same, 5,400 psi. If you have a shut-in well, formation pressure equal bottom hole. So the bottom hole equal formation pressure. Let's do it. I have here 5,100 psi from the side of annulus. So I need a back pressure, casing pressure, 300 psi. So this side is stabilized now. This side, the annulus side, is stabilized now. It's equal 5,400. What about the string side? You have a hydrostatic pressure 5,200 psi. So you need a back pressure just 200 psi. Okay. What is the value of shut-in drill pipe pressure represents? Represent what?
We can calculate actual bottom hole pressure, formation pressure based on this extra 200 psi.
Yes, the underbalanced value. So if I tell you the shut-in drill pipe pressure equals zero, that means I do not have a kick. I just have a gas inside the annulus, and the casing pressure will be with another value. For example, if you have a shut-in drill pipe pressure 0 psi, shut-in casing pressure 200 psi, that means you're overbalance. You still overbalance. Why? Because the shut-in drill pipe pressure value represents the difference between the formation pressure and bottom hole pressure, the value of underbalance. So it's 0. If it's 0, I'm overbalanced. But now this shut-in drill pipe pressure 200 psi. Shut-in casing pressure is 300 psi. That means the shut-in drill pipe pressure represents the value of underbalance. What about this? 300 psi. It's equal what? Equal 200 plus 100. This 200, the casing pressure represents the value of underbalance plus the hydrostatic pressure reduction, which is compensated by closing the well. So the hydrostatic pressure reduction due to entering the gas inside the annulus, which is compensated by more clothing from the side of annulus. Make sense? Does that make sense? Okay. Here, the bottom hole pressure. The bottom hole. Tell me the equation of the bottom hole pressure from your understanding.
Hydrostatic in the drill pipe plus shut-in pressure 200.
Shut-in drill pipe pressure plus shut-in drill pipe pressure plus the hydrostatic inside the string.
Drill pipe string.
Yeah, and also shut-in casing pressure plus the hydrostatic pressure inside the annulus. Yes. Why? Because the well now is stabilized from both directions. Look at this. Shut-in drill pipe pressure equal 200. Hydrostatic equal 5,200. The total is 5,400. Shut-in casing pressure 300. Hydrostatic 5,100. The total is the same, 5,400. So the well is stabilized, but you have a hydrostatic pressure in the annulus less than the hydrostatic pressure in the string, but it's compensated by more pressure from the casing pressure. Does that make sense? Okay. If I tell you why the shut-in casing pressure greater than the shut-in drill pipe pressure, what is your answer?
Shut-in casing greater than the drill pipe, right?
Yes.
Because of this gas in the annulus.
Because you have yes, gas inside the annulus, so you have a density less than, or a hydrostatic pressure less than the hydrostatic pressure inside the string, and this reduction in hydrostatic compensated by more closing, by more casing pressure. Okay.
Yes.
Okay. Okay. As you can see here, the bottom hole pressure in case of static equal the hydrostatic only. And in case of dynamic, if you have 2,000 psi coming from the pump, you will have a pressure losses till you have a large pressure losses across the nozzle of the bed, and you will still have APL inside the annulus. Bottom hole pressure in case of dynamic will be equal the hydrostatic pressure plus APL. Okay. So now we have a term here. Look at this. If I want to derive a mud weight from the bottom hole pressure static bottom hole pressure. If you want to derive a mud weight from this static bottom hole pressure, any pressure you want to convert it to mud weight, just take your mud weight and divide the pressure by 0.052 multiplied by TVD, as you know. It's very simple. And this is bottom hole pressure. Bottom hole pressure is static. So this mud weight will be static. And this is the first mud weight we will deal with this. We have a different mud weights in well control. We have a static mud weight, dynamic mud weight, maximum allowable mud weight, and fractured mud weight. We have at least 4 types of mud weights. Mud weight is static, mud weight dynamic, and maximum allowable mud weight, and keel mud weight. Okay. If you derive the mud weight from the bottom hole pressure static, it will be mud weight static. And if you want to derive a mud weight from bottom hole pressure dynamic, it will be mud weight dynamic, which is called what? Annular pressure equivalent circulating density, ACD. So ACD equal mud weight dynamic. For example, if I tell you the mud weight is static equal 10 ppg. And I have an APL 200 psi. So if you convert this 200 psi to mud weight and add it to your static mud weight, you will get the ACD. So the ACD, let's assume it's 10.3 ppg. And you have a leak of test, which is conducted on exploratory or wildcat well, exploration well. This wildcat well, we get from it the maximum allowable mud weight. If you mix this mud weight and drill with this maximum allowable mud weight, the well, your well will be fractured. So the maximum allowable mud weight is 10.2 ppg. And my question is, as you can see here, you can calculate the equivalent circulating density or your dynamic mud weight very easily. But what is the benefit from knowing this value, ECD? Yeah, I need your share.
We can evaluate if we're gonna have losses or fracture formation.
Yes. It's used to compare to the, or compared with the maximum allowable mud weight. If you still static, your mud weight is 10. It does not exceed the maximum allowable mud weight 10.2. So you will not fracture the formation in case of static. But if you operate your pump, what will happen? Your mud weight now that the well can see, it's 10.3. You exceed the value of maximum allowable mud weight. So when you're static, you will not fracture the formation. When you're dynamic, you will fracture the formation. So the value of ECD, it's used to compare to the maximum allowable mud weight. Okay. We have a simple equations, like if you change your mud weight, the pump pressure will be changed too. And also if you change the stroke per minute or your pump speed, the pump pressure will be changed too. So for example, if you have 2,600 psi pump pressure and you changed your mud weight 10 to 11 ppg, and you want to calculate the new pump pressure, it will be equal the old pump pressure multiplied by new mud weight divided by old mud weight. P new over P old equal mud weight new by my mud weight old. And let's calculate it. The new pump pressure, it will be 2,600. I think it's calculated here. It's solved here. Yes, solved it. Yeah. 2,611 by 10. This is the new mud weight divided by old mud weight. So this is the new pump pressure. And also, if you changed your stroke per minute from 80 to 100 stroke per minute with the same old pressure, you can get the new pump pressure by using the old pump pressure multiplied by new stroke per minute divided by old stroke per minute over or power 2. Don't forget it, please. So this is the new pump pressure. Let's discuss some questions about the previous part. Yeah, Mr. George, go ahead. I think this is the, yeah, I think this question is repeated, yes. What term means uncontrolled flow? Okay, uncontrolled flow out, yes, uncontrolled
flow out.
Yes. Yeah.
Force acting on area.
This is pressure. Force is acting by area. It's a pressure, yes. Mr. George.
What effect does increased pressure have on fluid density? What effect is increasing pressure on fluid density? It's decrease the fluid density. It does not affect the fluid density. It increases the fluid density.
We didn't explain this. Let's explain it now. If you increase the pressure on fluid density, what will happen? He's asking you about the ECD, equivalent circulating density. If you increase the APL, what is the new value of the fluid density? Will increase. Okay?
Increase, yes.
But if you increase the temperature, Increasing the temperature will increase the viscosity. It will decrease the viscosity. So it will lead to the barite settling or barite sagging. Okay? So your hydrostatic pressure will drop. So increasing the pressure on the fluid density will increase the fluid density. Increasing the temperature will decrease the fluid density. Make sense?
Yes.
Okay. So it increases the fluid density. What effect does increasing temperature having on the fluid density? It will reduce the fluid density. Yes. Yeah, Miss Anna.
Okay, what happens to bottom hole pressure when the pumps are shut off? Stays the same, declines, increases. Bottom hole pressure stays the same. I think it's gonna stay the same.
If you have your bottom hole pressure in case of operating your pump equal what?
Oh,
Equal
it's plus losses. Okay, so it's gonna decline.
Yeah. Yes. Mr. Roman.
What happens to bottom hole pressure when circulation is stopped during connections? B will decrease.
What happens to bottom hole pressure when circulating gas will decrease? I think it's the same idea of the previous question.
Yes.
Yeah. What changes in pump pressure will be seen after one complete cycle or after complete circulation if the mud weight is increased? Yeah, Mr. Josh.
Same or decrease, increase. The pump pressure will increase.
Yeah. Change the pump pressure will be seen after one circulation if the mud weight increases. So we have an proportional relationship between the pressure, between the pump pressure and mud weight and stroke per minute. So it will increase. Yeah. And here, this is the most famous question, one of the most famous questions in the IADC chart. Holding 1,200 psi at the surface will have the most, look at this, effect on mud weight on which well? We will, yeah, I need your share first. Yeah, your turn, Miss Anna.
Wouldn't they sign the survey?
Have you remembered the last question about the increasing the pressure on the mud weight? Increases the mud weight or decrease the mud weight? Increase the mud weight. Okay.
Yes.
Okay. But if you have 1,200 psi pressure holding or pressure applied or pressure holding on the shortest well. If you have a long open hole well like this, long open hole well, and you have 1,200 psi through this well, okay? So you have 1,200 psi, so you will have a pressure losses here, for example, 300 psi, and here across the BHA for 4,400 psi, and the rest will be 300, 400, and this 1,200. That means, just type, please, just type.
Самая короткая скважина 4500 TVD должно быть.
I'm sorry, please, sorry about this interruption.
I was saying it should be the shallowest well.
Shallowest well because you will have a high EPL, okay? A high EPL, you'll lose the pressure, and the rest of the pressure will be high after the bed, okay? So if you have a long well or a long depth, your EPL, for example, maybe 100 psi. Okay, but if you have a short well, your APL will be 300 psi. So increasing
But are we
this
talking? Sorry,
Yeah, go
are we
ahead.
talking? Are we talking about APL? Because I think it's about static condition, no?
About
Holding.
this
Static or dynamic condition? What is this condition?
He's asking about holding pressure. That means it's dynamic.
But what if I just shut the well and I have this 1200 psi on casing shut-in pressure on the drill pipe?
That means you're using the MPD, for example, and closing the or applying a pressure from the side of annulus.
Yeah, I mean, if we're talking about APL, it means here I'm using MPD circulating with a back pressure, right?
Yes,
Maybe
1000.
circulating through choke.
It's the same idea. If you're holding the 1200 psi, you get more pressure inside the annulus, so that's affect the mud density by increasing it. So the holding 1200 psi, it will affect, the most effect will be on the shortest well, as you know. Okay, it's the same idea. Even if it's dynamic or holding a back pressure 1200 psi.
So it will be B, second
yes,
answer,
yes.
correct?
Yeah, yes. The answer, shortest one. Correct. Yeah. The second question, TVD 6700 psi and measure depth. Yeah. Your turn, Mr. Roman.
Okay, so I will calculate 1 second. TVD. B, 10 ppg.
6766. L1052. Yes, I think 9.4 plus 10 6700 9.052. Yes, correct.
Correct.
Yes, 10 ppg. Okay. Your turn, Mr. George. About the APL also. ACD.
What is the CD? Just to give me a moment.
Okay. Yeah. Yeah. Yes.
10.5 B.
Yes. 10.5. Yes. Sana.
Okay. 35 divided by 42 in square, right?
Yes. 35. 42. 42 square.
You're multiplied by the pressure. 232. Well, it's B. If it's
answer.
rounded up.
35 divided by 42. 232. Yeah, 233 is rounded up. Right. Yes. Mr. Roman.
Okay, while circulating a kick, we are instructed to decrease pump rate. Okay. So strokes, divide 20 by 25. 0.8 power 2. Okay, 0.64. Now multiplying. Final circulating 320. Okay, by 320. 205 D.
The answer. It's rounded up also. Okay. Yes. So George.
While pumping at 50 strokes per minute, the standby pressure reaches 120, 1250. The previous standby pressure will increase B 1800.
B. The answer.
B.
Yeah. Okay. Okay. We have here theoretical topics like MPD, managed pressure drilling.
I have a question.
Go ahead.
So, for example, we discussed if our shut-in casing pressure is going to be more than shut-in drill pipe pressure. But for example, what if our shut-in drill pipe pressure is going to be more than the shut-in casing pressure, or they're going to be equal?
Yeah. In the ballooning formation, both gauges will be equal. And if you have a bottom hole pressure, if you have an influx below two sides, that means you have an off bottom. Your string is off bottom because you have the influx below two sides, casing and string. And if you have influx inside the horizontal well, both gauges will be the same. So we have if you have a casing pressure equal drill pipe pressure, shut in casing pressure equal shut in drill pipe pressure if you're off bottom and you have a kick. In the second case, shut in casing pressure equal shut in drill pipe pressure in the horizontal well. If you have an influx inside the or a kick inside the horizontal well, okay. But if you have a kick, look at this, and this kick is salt water. This kick is salt water entering the annulus. So this salt water increases the hydrostatic. So the casing pressure will be lower than or less than the shut-in drill pipe pressure. Make sense?
Okay, so we can assume, and from that I can say that my shut-in drill pipe pressure is going to be higher than the shut-in casing pressure only when I do have a salt water influx.
Yes.
Okay.
Okay.
In all other cases, I do always shut-in casing pressure more than shut-in drill pipe
Yeah,
pressure.
because the cake usually, or it's always it's always gas. It's always gas. The type of influx always gas. We assume this.
Okay.
But the casing pressure, shut-in casing pressure equal the shut-in drill pipe pressure. In the case of having a kick and your string of bottom. Okay. We'll discuss it in the gauge interpretation, but I will tell you. Look at this. If you have a kick inside the horizontal section, shut-in casing pressure will be equal shut-in drill pipe pressure. Why? Because the gas inside the horizontal section, there is no expansion. There is no expansion for a gas inside the horizontal section. There is no response. There is no effect or there is no effect on the hydrostatic pressure inside the annulus. Okay? So this is the first case of shut-in drill pipe pressure equal the shut-in casing pressure. And the second case, if you found the casing pressure equal shut-in drill pipe pressure, if your string of bottom if you have a gas and your string here of bottom, because the effect of gas will be on both. Okay, so if your bit of bottom shut-in drill pipe pressure will equal the shut-in drill pipe pressure. If you have a gas inside the horizontal section, shut-in drill pipe pressure also will equal will be equal the shut-in drill pipe pressure. Okay. we have here a theoretical topics like MPD, managed pressure drilling. It's mentioned in the IADC will sharp as the theoretical topics. There's no more calculations inside it, and also the cake tolerance. This topics is not included for your information. It's not included in the syllabus of the IWCF, MPD, and cake tolerance. It's not included in the syllabus of the IWCF. Here in the MPD, managed pressure drilling, we have a different type of MPD or different methods for MPD. But the method which is mentioned in the syllabus of the IADC will sharp called surface back pressure, SPP. SPP, surface back pressure. We have two types of window. We have here a large drilling window when you have a fracture pressure and formation pressure here. Large drilling window. In case of your bottom hole pressure is static, it's equal to hydrostatic pressure only. And in case of dynamic, your bottom hole pressure dynamic equal bottom hole pressure static, which is hydrostatic plus the ABL or the friction losses. So this is the conventional drilling. In conventional drilling, bottom hole pressure in case of static equal hydrostatic, and in case of dynamic equal hydrostatic plus ABL. And we have a large drilling window in conventional drilling. Look at the layout. The return, your circulation system from the pump inside the string, the annulus, and the return above the BOP to the return or to the flow line, then to the shell shaker. So it's open to atmosphere. Flow nipple. It's open to atmosphere here. If you want to look at the bottom hole pressure and want to increase your bottom hole pressure, you do not have more choices like MPD, like surface back pressure. In the surface back pressure in MPD, you can make a manipulation or manipulating, okay, because you have a different factors to control. But here, in case of drilling, I have only ABL and hydrostatic pressure. In case of connection, during connection, you lost this circulating friction, which is ABL. You lost it. So the potential of entering the connection gas during connection, it's high. Here, you cannot increase your bottom hole pressure in case of connection. You don't have the ABL, but you have only the hydrostatic. Resuming your drilling again or return to drill, the hydrostatic plus ABL in case of drilling. If you want to increase your bottom hole pressure, look at this, increase to bottom hole pressure. The conventional way to increase your bottom hole pressure, you will increase your mud weight. You will increase your hydrostatic pressure. Okay? So the conventional way to increase the bottom hole pressure in case of conventional drilling, just increase your mud weight, increase your hydrostatic pressure. No factors more. But in case of MPD, which is a closed loop or closed system, the benefits of using MPD, it enables us to drill with more consistent bottom hole pressure, and we will discuss it. And also aids to mitigate the pressure-related non-productive time events and enables well to be drilled within tight window. Let's discuss it in details. Look at this. If you have this formation pressure and this is the fracture pressure, in conventional drilling, if this is the fracture pressure, if this line is a fracture pressure, the conventional drilling, it's not suitable to drill in this window, the fracture pressure and bore pressure. But in the MPD, it's suitable to drill even if it's more or even if it's over the line of the formation pressure like this. I can create a bottom hole pressure over the formation pressure, but it's not it cannot be applied by the conventional drilling to do this or to drill in tight window. So we must use the MVD, a closed system. Look at the layout. The bottom hole pressure in the closed system equal the hydrostatic pressure plus back pressure. In case of static, using closed system MVD. In case of dynamic, hydrostatic pressure, back pressure, and ABL from the pump. This is the layout, closing system. Here we have the same well-controlled circulation here. This is a rigid choke manifold. The same, but we have an equipment over the conventional drilling. We will discuss it. We will discuss each equipment in details. Don't worry. The circulation here, it's a closed system or closed loop. The return is coming from the annulus over this flow line through the RCD, rotating control device. It's an MBD equipment. And here we will have an orbit valve. This layout, it's related to the syllabus of the IADC will sharp. It may be changed. It may be changed. Company policy specific, no problem. But this layout, it's according to the syllabus of the IADC will sharp. So the return is coming through the closed loop through the flow line, and here we will have an orbit valve. We'll discuss about the benefit of this orbit valve, and we have here an MBD choke, or called a drilling choke. So we have a rigid choke. It's through the well-controlled circulation in case of you have a kick, but here we have an MBD choke, which is a drilling choke, flow meter on the same choke manifold of MBD, and also relief valve. We'll discuss the benefits of each one. Then also you have in the same layout a line here attached to RCD if you want to operate the pump of the trip tank over the well, like this. If you want to operate the pump of the trip tank over the well, we have here flange attached to the RCD to operate the pump of the trip tank. So this is a closed loop. In the conventional drilling, it's open loop. Over the BOP, we have RCD. The return is coming through from the annulus through the RCD to the flow line, having an orbit valve, MBD choke, and relief valve. And here we have a pump out upstream. This is choke manifold. This MBD choke manifold. Why? In case of connection or in case of drilling, if you want to apply a back pressure, I need a pump in case of connection to pump out upstream the choke manifold to apply a back pressure over the well. And this is a relief valve. This relief valve is used to protect the low rated working pressure in this closed loop. Okay, let's discuss the bottom hole pressure cases. As we mentioned, in case of drilling in MBD, you have a hydrostatic pressure, circulating pressure, ABL, and back pressure. If you want to make a connection, you lost this ABL, but it's compensated by more back pressure. More back pressure. So the bottom hole pressure will be consistent. Yeah, will be consistent, will be constant. In case of resuming a drilling again, you want to increase your bottom hole pressure. If you want to increase your bottom hole pressure, Can we do like a conventional drilling, increasing your hydrostatic pressure? No, no, no. Why? Because I have many factors to make a manipulation. Like what? Like a hydrostatic pressure, APL, and back pressure. The easy way to increase your back pressure. So the MPD allows me to what? Allows me to drill with low or very, very low hydrostatic pressure or using very low mud weight. Why? Because it's compensated by a back pressure. Does that make sense? Okay. Okay, let's have a look on this video. Okay.
Take control of your onshore drilling operations with purpose-built and cost-effective closed-loop technologies. The Weatherford Pressure Pro control system enables basic capabilities for managed pressure, underbalanced, and flow drilling operations, so you can work safer, faster, and more economically. The system features a Weatherford Safe Shield rotating control device, or RCD, which creates a pressure-tight barrier in the wellbore annulus to contain and divert drilling returns for enhanced safety. Our Safe Shield 5M model offers design improvements in liquid and gas drilling environments, including a short stack height, large through-bore diameter, and high pressure ratings up to 5,000 psi. A remote latching system and a self-lubricating bearing assembly both eliminate the need to work below the floor. A rotating flange reduces rig-up time, and an interchangeable bowl adapts to a range of flange configurations. The Pressure Pro system also features the electric set point choke, which provides precise semi-automated pressure control that reduces manpower. As pressures vary in the wellbore, the choke automatically adjusts its position to maintain the pressure set point. Our OneSync software platform integrates with the Pressure Pro system so that you can create ramp schedules to increase the accuracy of wellbore pressure management during connections. With the Weatherford Pressure Pro control system, you can proactively manage wellbore pressures to mitigate well control incidents, minimize non-productive time, and reduce mud costs.
Okay. As we mentioned, this closed system may be varying from the company to another company, but we discussed the layout which is set by the IADC wheel chart. Here we have an additional equipment over the conventional drilling in MPD, like a rotating control device. This rotating control device. Yeah, this rotating control device, the maximum rated working pressure of it, it's 5,000. The maximum rated working pressure of the MPD of the rotating control device is 5,000. And for your information, this MPD, even if you apply pressure and even if you use it closed, it's not considered as a barrier. According to the API, it's not considered as a barrier. Like a diverter. It's used like a diverter, okay? But according to the API, RCD, rotating control device, it's not considered as a barrier. It's not having the same rated working pressure of POP, okay? Look at this. This rotating control device consists of, look at the components of it on this video. It consists of a rotating head or ball and bearing assembly and clamp and sealing element. Yeah. Yes. This is a sealing element. This is rotating head, bearing assembly in the rotating head, and the clamp. And this flange suit to the rig. Okay. This is a rig up of RCD rotating control device over the annular. This is lowering the RCD bearing to the RCD ball or to the rotating head. I think we missed Roman. Mr. Roman?
Yeah, sorry, I got a blackout at home.
No.
Electricity blackout, just reconnected, yes.
No problem. Okay. This through the lowering RCD bearing to RCD ball. Okay. Okay, this is during the rig up and function test of the RCD. Running tool of the RCD sealing element and RCD assembly, bearing assembly. And it will be run inside the rotating head or the RCD ball or rotating head. Open, look at this, the clamp is open. The sealing element and rotating or RCD bearing is set in its place inside the rotating head. This is the component of RCD, rotating control device. It enables you from reciprocating and rotating and also circulation through the closed loop. And this is the sealing element and how to change the sealing element. Look at this. The first equipment we have talked about, the RCD. The second and third equipment, it's MBD and MBD choke. Here we have two drilling choke on the same choke manifold. This is a backup. This be drilling choke or MBD choke. MBD or drilling choke, both are the same. It's used to hold back pressure during connection or during drilling. And here we have a careless flow meter. We'll talk about it later. This pump, MBD pump, must pump out upstream this MBD choke because during connection we need to keep the bottom hole pressure constant. This is bottom hole pressure constant. To keep bottom hole pressure constant after losing or after the loss of the ABL, the pump must pump out. This auxiliary pump of MBD pump used to pump out upstream the choke during connection to maintain the bottom hole pressure constant to compensate the losses of this APL. Okay. And here we have a relief valve to protect the equipment that had a lower rated working pressure in this closed loop. And here we have an orbit valve. And the benefit of this orbit valve is to hold the pressure during connection. During connection, to hold the same pressure during the connection. Why? Because your rig pump is off. Okay. Through applying the back pressure, by applying the back pressure, maybe you will have a pressure or a return from the string, inside the string, due to your tubing. And maybe someone say, we have a float valve to prevent the backflow through the string. But the float valve, as we mentioned, it's not a tested barrier, so it's not considered as a barrier. In the MBD, we have inside the string non-return valve, but this non-return valve is a barrier. In the IWCF, we used in the underbalanced drilling or MBD something called dart sub. This dart sub it's located at the last part of BHA. And before trip out of hole, we drop this dart inside this sub, or we drop it inside the string and circulate till it's set in its place inside this sub. This dart sub or non-return valve prevents the backflow inside the string while using the MBD. And here we have a careless flow meter. This is very sensitive flow meter. It discovers the gain and losses even if you have, for example, 18 gallon. 18 gallon. Yes, 18 gallon. It's not 1 barrel, 18 gallon. Very sensitive flow meter. It's mounted on that choke manifold. This is the shape of the photo of the mass flow meter. Okay, careless flow meter. And yes, and we have here ICU. It's the brain of this system. All data is acquired and direct to it. And here we have an HPU, considered as the SWACO unit, but it's located on the skip. Okay, yeah, it's an integral part of MBD system that provides the direct means to move the choke under controlled MBD software. And here we have the HMI, human machine interface. We have a real-time drilling acquisition and control compression and human machine interface, including the control operator panel and drillers panel and remote panel. Okay. Let's take an example to understand the MBD deeply and how it gives us a solution for the well-controlled situation very quickly. This is a normal operation which appears on the rig sense of MBD. Here we have the flow. This is a normal situation. Flow in must be over the flow out, one line, like this. And here we have the surface back pressure, bottom hole pressure, and choke position. This is the normal operation. Look at this. In case of losses, the flow out will be greater than or less than the flow in. So to solve this problem, I need to open the choke to decrease the surface back pressure, to decrease also or reduce the bottom hole pressure. But in case of gain, look at this, gain detected. The flow out here, this is a normal. The flow out is greater than the flow in. So that means we have a kick. How can we solve this problem? By the MBD, close the choke to increase the back pressure and bottom hole pressure, or decrease. Yeah, which one?
Close the choke.
Close the choke. If you close the choke like this, what will happen to the bottom hole pressure? You increase the bottom hole pressure and you increase the back pressure. Look at this. The flow out return to its original shape again, original value again, over the flow in. You imagine. In case of conventional drilling, if you have a flow out greater than the flow in, that means you have a kick. You have a kick. In this situation, in conventional drilling, if you have a kick, you will prepare, you will record the shut, you will shut in the well, record shutting casing pressure, shut in drill bit pressure, bit gain, TVD. Then you will prepare your kill sheet. Then you will prepare your well to be killed. Killing procedure. But in MBD, you solved a kick problem in just maybe 41 minutes to 42, it's less than 1 minute. You solve the cake problem in 1 minute. Okay? Make sense? Okay. Let's discuss the questions of the MBD. Mr. George. Yeah.
What do you calculate to keep enough pressure on the well when in a static state, non-circulating? Mass minus hydrostatic of the well, hydrostatic pressure of the mud in the well, plus back pressure on the rotating control device, hydrostatic pressure plus FAD plus back pressure, mass minus B, hydrostatic pressure of the mud in the well, plus back pressure of the rotating control device?
Yes, in casing of static, using MBD, like as we mentioned, in case of static, using MBD, hydrostatic pressure plus back pressure, yes. In case of dynamic, you have the increment of APL on. Yeah. Miss Anna?
Which are not main components of an RCD system. Bearing assembly.
Bearing assembly. Look at this.
Yeah, because for the you have a rubber to seal against the pipe, right? Then you do have.
This is Miss Anna, please. This is the RCD bearing, and this is the bearing assembly. Okay.
Oh, it's
This
called
is
bearing
the
assembly.
sealing element, and this is a bearing assembly. Okay.
Okay.
And this is the rotating head. Okay.
Yes.
This is the component of RCD: rotating head, bearing assembly, and sealing element. So, which is not component of RCD, the orbit valve on the flow line.
Okay, of RCD. Okay. Yeah, I've misunderstood about the MPD as a whole thing.
Yes. If the question is the component of MPD or closing loop, you will select
Okay, then orbit something.
or
Yeah, the
orbit
last
valve.
line.
Yes. Yeah, it's not component of the RCD, but it's component of MPD. Yes. Yeah. Mr. Roman?
Okay, rotating head used while MPD drilling gives us the ability to safely accomplish what while drilling? Rotating head. All of above. D.
Keeping formation pressure over bottom hole pressure all the times? No, not all the time.
Formation pressure, sorry. No.
Allow?
Not all the times. Yeah, allows.
Yes. Allows lower mud weight.
Lower mud weight, B.
Yes. Close on the well in case of cake? No, it's not applicable by the MBD. Okay. How can you tell how much pressure the rotating is holding? If you want to know how much pressure the RCD is holding,
It was mentioned 5,000 rating.
Yeah. This is the maximum, and it's not considered as a barrier. Yeah. If you want to know how much pressure this RCD is holding, just open HCR and read the casing pressure. Okay. Open the HCR and read the casing pressure to know how much pressure the rotating head is holding. Yeah, Mr. George.
Why is a rotating control device not part of the well control equipment if primary well control has been lost? As part of the primary well control equipment, it does not have the same pressure rating as a BP. It is designed to contain well pressure to kill a well. None of the above. None of the above.
We have a correct answer here. B answer.
BB.
Yeah, it doesn't have the same rated working pressure of the VOB. It's B answer.
Okay.
Okay. With rotating ahead an orbit valve, what level of underbalanced drilling can we safely accomplish? Miss Anna.
Okay, let me read first. Okay, underbalance, meaning that our formation pressure is more than the bottom hull pressure, right? So with the managed pressure drilling, we can keep bottom hull pressure equal to formation. So I would say A.
To compensate
But
for ECD, I think.
yeah, B, I think, yes. With a rotating head and orbit valve, what level of underbalanced drilling can we safely accomplish? It's compensate losses of ECD by closing the orbit valve during connection to hold the back pressure. But MBD is used to keep the bottom hole pressure nearly equal the formation pressure. It's also the correct answer, yes. But he's asking you about the orbit valve.
And the
Okay.
orbit valve is used only for connections.
Yes, yes. Okay. Why should pressure relief valve be installed in MBD system, Mr. Roman?
D, to protect low pressure equipment.
Yeah. Low pressure equipment. Yeah, Mr. Josh.
What are the benefits of using a PD while drilling a well? It enables a well to be drilled with more consistent BHP. It aids to mitigate pressure-related non-productive time events. It enables a well to be drilled within a tight window. D, all of the above.
Yes, these are the benefits of the MBD, yes. Yeah, Miss Anna.
And I would say C.
The answer, my name is yes. Yes, the same. Yes, okay. And that's all the above. Okay. Let's discuss about the kick tolerance, and then we'll take a break, okay? Just kick tolerance. It's a very simple topic inserted also. It's theoretical here, no calculations. The calculation of kick tolerance, it's not included in the syllabus of the IADC will sharp. No calculations for a kick tolerance. What's the meaning of kick tolerance? Yeah, I need your share, Mr. Roman.
Kick tolerance is the maximum volume of kick which we can take and circulate out without breaking the casing shoe, weakest point, the casing shoe.
Yes, perfect. So it's the maximum kick size that can be taken and circulated without fracturing the weakest point, which is the fracture, which is the casing shoe. But here, at given what? At given depths, because it's a blend, at given depths, and also at given kick intensity. What is the meaning of kick intensity? Kick intensity means the difference between the formation pressure and the hydrostatic pressure, or maybe the blend underbalanced value. The blend underbalanced value. So more you increase or more the kick intensity increases, the kick tolerance will decrease. More kick intensity increases, kick tolerance decreases. We have an opposite relationship between the kick intensity and kick tolerance. And also, if you increase the depth or increase your mud weight, what will happen to the kick intensity? What will happen to the kick tolerance, sorry? Well, decrease also.
If we increase mud weight, yeah,
Yes.
it will decrease.
It will decrease. Okay, why? Because we have a relationship between the MASP and kick tolerance. The MASP is the total of kick tolerance budget. Okay, and here the MASP, look at this. mass equal what? Mass equal the fracture pressure minus the hydrostatic. If you increase your mud weight, what will happen to this mass? Will decrease. Okay, so we have an opposite relationship between increasing the depth, or increasing your mud weight, or increasing the kick intensity with the kick tolerance. If you increase the depth, increase the mud weight, increase the kick intensity, land the kick intensity, your kick tolerance will be decreased. For more understanding, as we mentioned, the shot and drill by pressure represents the value of what? The value of underbalance. And if the casing pressure, if the shot and drill by pressure 500 psi, that means this is the kick intensity. The difference between the formation and hydrostatic, or the formation and bottom hole. This is the value of underbalance. And if you have a casing pressure 600 psi, 600 psi, that means what? That means I have 500 psi underbalance or kick intensity, and size of kick or gas size bubble can replace mud in equivalent to 100 psi. Make sense? Does that make sense? But you know the maximum casing pressure called what? Called mass. So if I take the difference between the mass and the shot and drill by pressure, I will get the maximum gas size. Make sense? Does that make sense? Okay, look at this. This is 500 psi. This is the kick intensity, shot and drill by pressure. And this shot in casing pressure. Here, if this casing pressure 600 psi. Shot and drill by pressure means the underbalanced value. The underbalanced value called kick intensity, which is the difference between formation pressure and hydrostatic pressure. Okay? The casing pressure is 600 psi. Casing pressure equals 600 psi. If you take the difference between shot in casing pressure minus shot in drill by pressure, you have 100 psi. This 100 psi means bubble can replace mud in equivalent 100 psi. Till this point, does that make sense? Okay. If you have the mass 1000 psi, the casing pressure can approach the mass till it be 1000 psi. If you take the difference between mass minus shot and drill by pressure, that means you still have 500 psi. It means the gas bubble can replace mud in equivalent to 500 psi before fracturing the show. Does that make sense? Miss Anna, understood or not?
Yes.
Okay.
Just
So-
one question.
Go ahead.
Why we are comparing casing side 1000 psi with drill pipe shot and pressure?
I'll tell you. Because the mass equal what? Equal the value of shot and drill by pressure, the value of getting underbalance, plus the maximum kick size. So I need the maximum kick size. Why? Because in the calculation, it's not included by the IADC will chart, but I will mention it. In the calculation of TVD, maximum TVD of kick, let's assume it's a gas. the maximum TVD of the gas equal mass minus shut-in drill pipe pressure. Why? Because this is a pure underbalanced, and this underbalanced plus maximum gas size. The hydrostatic pressure, the maximum hydrostatic pressure reduction due to maximum gas size divided by the gradient of mud weight minus the gradient of gas. Look at this. The units of this gradient psi per feet, and the unit of this will be with psi. You will get the maximum TVD. So we compare the mass to the shut-in drill pipe pressure, because the mass equal what? Equal the maximum gas size plus the maximum kick intensity, or the underbalanced value, which is represented by the shut-in drill pipe. I don't need the kick intensity. I want to calculate only the maximum kick size. The maximum kick size, how can I calculate it? Just remove the value of underbalance, you will have the maximum kick size. Does that make sense? Okay. When to calculate the kick tolerance? Yeah, it's theoretical. It's not mentioned by the IADC wheel chart, but after leak of test, we can do it. Interval through the whole section, we can calculate it. If any factor of mud weight it changes, we can calculate it. And if the geometry of each or the geometry of well is it changed, we can calculate it again. To calculate the kick tolerance, we must have this. To calculate it, we need the kick intensity. We assume the kick intensity value, and it's different from company to another. Maybe 0.5 BBG get under balance. Maybe 0.6 BBG you will get under balance. And the kick dips, and the dips that the kick will happen at, and the following element determine the magnitude of the kick tolerance. The calculation, as we mentioned, the calculation of kick tolerance, it's not included in the syllabus of the IADC wheel chart. Okay, Mr. George, what is the kick tolerance?
The required pressure rating of the maximum tolerable surface pressure. I think the maximum volume of inflation in the blasting can be taken a certain depth without exceeding friction. Without giving depths. C, the maximum volume of inflation. Yes.
Yes, C.
Can be taken.
Yeah, Miss Anna.
Okay, let me read first. B.
B answer. Yeah, for a given kick intensity and particular depth, yes. B answer. But before calculation the kick intensity, kick tolerance, we must assume the kick intensity and the given depth and planned mud weight. Okay, and knowing the value of mass. What is meant by the kick tolerance at 25 barrel, Mr. Roman?
Yeah, this is A.
A answer. Based on choosing kick intensity, a gas kick 25 barrel maximum that can be shut in and circulated without gas. B answer. A answer. Yes, Sir Josh.
As you drill the open hole deeper, what happened to the maximum volume gas of kick that can be taken on bottom and circulated without breaking the formation from all the information branch stay the same. As you drill can be taken and bottom circulated.
If you increase the depth what will happen to the kick tolerance?
It's decreased. Decrease.
Yeah.
B.
Yes. Sana?
I think it will increase.
If you increase the kick intensity, what will happen to the
Decrease.
kick tolerance?
Decreases.
Will decrease. Okay? Miss Anna, look at this. If you increase this value, kick intensity, consider it as shut-in drill by pressure. Make sense? Shut-in drill by pressure is the underbalanced value, is the kick intensity. Okay? But if you increase the shut-in drill by pressure in this law or in this equation, if you increase this, what will happen to this? TVD of gas will decrease. Okay? So the kick intensity, if you increase it, or if you increase the depths, the kick tolerance will decrease. Okay? We have an opposite relationship between the depths and the kick intensity with the kick tolerance. Look at the graph. We have here the kick intensity. And this is a kick volume or kick tolerance. It's opposite relationship as you can see here. Okay? And for each kick intensity, we have a kick volume. Yeah, Mr. Roman.
Okay, let me read this one.
Yeah, read it. Take your time.
Okay, so 1 ppg, we're looking at this at the right axis, kick intensity, then we extrapolate, and it looks like between slightly above 15, which is 17, right? The last.
Yes, 17. Very close to 17. It's between
Yeah, 17.
15 to the 20, but it's very close to 15. Yes, it's 17. Not 20. Yes. Yes. And here, Mr. Roman, Mr. George.
Drill shot in 2.5 ppg kick with a 20 barrels gain using the kick tolerance window below. Can the crew successfully shot in and circulate the kick out from without fracture and one weak point? So
Here we have 25, 2.5, and 20 barrel. Okay, 2.5.
2.5.
So this point, the intercept is here. Okay. Yeah. Can you can you shorten the well on 20 barrel with this kick intensity? This is the 20 barrel kick tolerance with kick intensity 2.5. This is the shut-in line. So I can shorten. Okay, but look at this. Can you circulate? No, you cannot circulate because it's out of this line. Make sense?
Yes.
You can shorten, but you cannot
Yes,
circulate.
I can, but not circulation. So
yes,
answer
no
is B.
Yes, yes, no. Okay. Any question?
No.
Okay, let's take a 30 minutes break, then we'll come back to resume our presentation again. Okay?
Okay.
Okay.